Hello everyone. Today we will talk about volcanoes. Volcano system is like a plumbing system that through which the magma came to the surface of the earth. The magma is from the asthenosphere. Because magma is molten rocks, its density is less than the rocks. Therefore, when magma is in the lithosphere, it migrates upward for light density. There is the magma chamber feed the volcanic system. Volcanic activity empties the magma chamber, and the chamber fills up with the source from a asthenosphere. The magma rises through central vent and branches off side vents. The central vent serves as the conduit where surrounds its mouth the Earth's surface. Lava and volcanic rocks accumulate to form volcano. Magma also forms side dikes and silts through the side vents. Sometimes the side vents also reach to the surface of the Earth, and it is where lava spills. Like igneous rocks, lava can also be classified into mafic, intermediate, and felsic lava. Mafic lava is basaltic lava. Its eruption temperature is very high, up to 1000 to 1200 degrees Celsius. Because of its high temperature and low silica content, the viscosity of the basaltic lava is very low. Therefore, the basaltic lava eruptions rarely explosive. Lava overflows the plumbing system of the volcano and flows downhill fast and far. When the eruption takes place on land, usually we're near the mouth of the volcano, when the lava contains a considerable amount of gases, the viscosity is low. The lava solidifies as pahoehoe. Pahoehoe is a thin spread layer of lava deposit. Because the surface solidifies fast when the lava was still flowing below the surface is dragged and twisted with coiled folds. When the basaltic lava flows further in distance, the gas content decreases in the lava, and the viscosity increases. As the lava flow slows down, its flow is thicker and its surface becomes rough. The deposit of such a basaltic lava flow is called aa. Hawaiian Islands are famous for its basaltic lava deposit. Both pahoehoe and aa are Hawaiian words. When the basaltic lava eruption occurs underwater, it forms pillow lavas. The lava cools fast when it's in contact with water, but its interior cools more slowly. Therefore, the pillow lavas have a glassy surface and a crystalline interior. Intermediate lava is called andesitic lava. Its eruption temperature is lower than that of the basaltic lava, which is less than 1000 degrees Celsius. For its relatively low temperature and relatively high silica content, the andesitic lava is very sticky and flows slowly. The sticky andesitic lava can plug up the throat of the volcano. When the lava meets groundwater and the seawater and generated a large amount of gases, which can blow off the plug and the top of the volcano. Therefore, the eruptions of andesitic lava are commonly phreatic explosions and destructive. Felsic lava is also called rhyolitic lava. Rhyolitic lava has the lowest eruption temperature, which is 600 to 800 degrees Celsius, and the highest silica content. Therefore, rhyolitic lava is very sticky. It takes a high content of gases, which lowers the viscosity for rhyolitic lava to migrate and reach to the surface of the earth. When the rhyolitic lava migrates to the surface, the pressure reduces. So small bubbles will form in the deposit, which is the vascular texture. Pumice is the typical deposit of rhyolitic lava, and it has the classic vascular texture. When the rhyolitic lava cools fast without crystalline structure, an obsidian will be formed. Besides, lava flow directly crystallize and deposit on the surface of the earth. Pyroclastic deposits are also major volcanic rocks formed from volcanic eruptions. Pyroclastic deposits include volcanic ejecta and pyroclastic flows. Volcanic ejecta consists of materials directly ejected into the air from the volcanic eruption and deposited on the Earth's surface. The ejected materials can be fine-grained, which is less than 2 mm in diameter, and after deposition, it is called volcanic ash. The ejected material can also be very large in size, fragmented blobs of lava ejected into the air and cools in flight. These are called volcanic bombs. Pyroclastic flow deposit. Pyroclastic flow is similar to the volcanic ejecta materials, such as hot ash, dust, gases, and lava ejected from the volcanic eruptions. The transportation of a pyroclastic flow is rolling downhill. The solids are buoyed up by the hot gases, so there is a little friction, and the pyroclastic flow can transport fast at a very high speed. After deposition, the hot, sticky materials will become welded together. If the material is fine-grained, it is called volcanic tuff. If the material if the material contains both fine and coarse clasts, it is called volcanic breccia. Now let's talk about the eruption style and the volcanic landforms. The eruption style of a volcano is decided by the chemical composition and the gas content of the lava, as well as the environmental conditions. The most common eruption styles are central eruptions. With central eruptions, different landforms can be formed. First, let's see the shield volcanoes. Shield volcanoes are formed by accumulating thin basaltic flow that run off the central mouth of the volcano. A good example is the Mauna Loa on the Big Island in Hawaii. The hill slope of Mauna Loa is very gentle, with a shield-shaped volcano. It forms by accumulating thin sheets of lava basalt for about 1 million years. Volcanic domes. Unlike basaltic lava, felsic lava are very viscous, sticky, that can barely flow. Felsic lava often produces a volcanic dome, which is a rounded, steep-sided mass of rock by squeezing out lava from the central vent with almost no lateral spreading. Because of the high viscosity of the felsic lava, the dome often plugs the vent, traps gases, and builds pressure. So subsequent explosive eruptions associated with the volcano domes are common too. Mount St. Helens in Washington state is a good example of volcanic dome. Cinder cone volcano is characterized by relatively steep angle of hill slope. The steep hill of volcano is built up with debris of pyroclastic discharged from central vent, and the cone of the volcano is with a clastic concave shape. Stratovolcanoes are characterized by alternating of lava flow and pyroclastic deposits. The volcano emits lava as well as pyroclasts, and the deposit of lava flow and interbedded with pyroclasts. and the deposit of lava flow are interbedded with a pyroclast. The hill slope is a stratovolcano, is also in concave shape. A famous example of the stratovolcano is the Fujiyama in Japan. Crater. Crater is a bowl-shaped pit found at the summit of most of the volcanoes. During an eruption, the upwelling lava overflows the crater walls. When the eruption ceases, the lava that remains in the crater sinks back into the vent and solidifies. The crater later becomes partly filled by debris that falls back into it. Sometimes the crater wall caves in and the crater becomes bigger than the vent in diameter. Calderas. A caldera is formed when underlying magma chamber cannot support its roof and the overlying volcanic structure collapsed. It is a large, steep-walled, basin-shaped depression. The most famous example of a caldera is the Yellowstone volcano. All the different structures and landforms of volcano we discussed above, including shield volcano, volcanic dome, cinder cone volcano, stratovolcano, crater, and calderas, are central eruption style volcano, which means that the volcanic materials are erupted from a single central vent. There are also eruptions through cracks, which is fissure eruptions. Fissure eruptions are the largest eruptions on Earth. Volcanic materials erupted from large, nearly vertical cracks in the Earth's surface that are of kilometers long. Fissure eruptions are the main style of volcanism along mid-ocean ridges. Volcanic systems are the most interactive system in the lithosphere with the hydrosphere and atmosphere. During volcanic eruptions, gases including water vapor, CO2, sulfur, sulfur dioxide, nitrogen, hydrogen, carbon monoxide, and chlorine are all emitted from volcano. Even after eruptions of pyroclasts ceased, the emitting of gases are still continuous from the central vent and other small vents of the volcanic systems. It is called fumarose. The emitted gas such as sulfur and sulfur oxides, chlorine, can dissolve in water easily. Small amount of sulfur in water can fertilize the soil and the lakes. In addition to emitting fumaroles, significant hydrothermal activities underground do not stop between the eruption events. Circulations of water through hot volcanic rocks and magmas continues. A geyser is a hot water fountain that emits steams with great force. The best known geyser in the United States is the Old Faithful in Yellowstone National Park. Besides the geyser, groundwater in the lakes, the atmosphere temperature and the climate can be influenced by volcanic eruptions. Though volcanic eruptions release a great amount of heat into the air, the volcanic ash, dust, and aerosol emitted from the eruptions can stay suspended in the atmosphere for a long time, and they can block and reflect the radiation from the sun. Therefore, the climate will become cooler. Huge volcanic eruptions in the geologic past were one of the major factors that drove climate to cooler conditions into icehouse ages. Now let's examine the global distribution patterns of volcanisms. Most of the volcanoes are located near convergent plate boundaries. The rest are located at the divergent plate boundaries. Rarely, there are volcanoes located in the interior of plates. The majority of the volcanoes are located at the convergent plate boundaries. The most lava eruptions takes place at the divergent plate boundaries, located at the spreading centers of the mid-ocean ridges. The seafloor spreading is facilitated by the basalt factories at the mid-ocean ridges. In the past 200 million years, the mid-ocean ridges produced all the basaltic oceanic floor that is on the Earth's surface today. Near the spreading center of the oceanic plates, seawater is heated by the newly formed basalt and the deep upwelling magma. The heat also drives the circulation of the seawater through the hydrothermal activities. Hydrothermal activities leach minerals and other elements from the newly formed crust, injecting them into the oceans. These elements contribute as much to the seawater chemistry as the material components dumped into the oceans by all the world's rivers. Metal-rich minerals precipitate out of circulating seawater and form ores of zinc, copper, and iron in the shallow parts of the oceanic crust. The ores formed when seawater sinks through porous volcanic rocks, is heated, and leaches these elements from the new crust. When the heated seawater, enriched with dissolved minerals, rises and re-enters the cold ocean, the ore-forming minerals precipitated. The hydrothermal activities also added nutrients to the seawater and feed the colonized of organisms whose energy comes from Earth's interior rather than the sunlight. In the oceanic system at the convergent plate boundaries, their magma chambers are generated by fluid-induced melting. Because the subducted oceanic plate contains sedimentary rocks rested on the seafloor, these sedimentary rocks serve as lubricants when the plate is subducted. The clay-rich sedimentary rocks releases water once it is heated at a certain depth during subduction. The extra water in the system can reduce the melting points of surrounding rocks, therefore produce melts to feed the magma chamber in the overriding plate, which facilitated the volcano on the overriding plate. Along the subduction zone, a chain of volcanoes can be formed. If the overriding plate is a continental plate, the volume of the continental plate will be increased due to magmatisms. If the overriding plate is an oceanic plate, the chain of volcanoes will be formed. The chain of volcanoes will form an island arc. Other than divergent and convergent plate boundaries, volcanoes are found in the interior of plates. Scientists hypothesized that this type of volcanoes are formed because of hotspots and mantle plumes. Hotspots are hot solid material rising in narrow jets from deep mantle called mantle plumes. When the solid material brought up to the shallow depth, it begins to melt and produce magma. The magma penetrates the lithosphere and erupts at the surface to form volcanoes. The current position of a plate over a hotspot is marked by an active volcano, which is inactive as the plate moves away from the hotspot. The plate motion thus generates a trio of extinct, progressively older volcanoes. In the picture, Yellowstone calderas fit the pattern well, yielding a rate of movement of the North America plate over the hotspot of about 25 mm per year for the last 16 million years. In the last, I want to show you the global large igneous province distribution. There are large igneous provinces on the Earth's surface mark the origin of fissure eruptions. Enormous large volume of flood basalt is deposited at these areas. The flood basalts are released in very short period of time. The releasing rates are comparable to the sum of all the mid-ocean ridges on Earth. How were the large igneous provinces were originated is a mystery for geologists. Some hypothesized that they were formed during the beginning phase of the hotspots, where first the turbulent magma from new mantle plume rose to the surface of the Earth and erupted in flood basalt. However, this hypothesis is disputed by some scientists who observed that large igneous provinces are often related to pre-existing weakness zones in the lithosphere. So it might be formed by convective processes localized in the upper mantle. To figure out the mechanism that formed the large igneous province, there's still a lot of research need to be done. So it's all I want to talk about the volcanoes, and see you next time.